Alrighty, so we are back from break and we are left here in piecewise functions. This is the last part of section 1.4 before we move on to 1.5. So let's talk about the different, the definition of what a piecewise function is. So the definition of a piecewise is when a function is defined by different functions or different pieces of its domain, it's called the piecewise function. So notice how on the left side, we have three different functions. We have a quadratic function, we have a constant function of y equal 2, and we have a line of y equal x plus 2. But they live in different regions. So this quadratic lives where x is less than 0. So to the left, you're at 0, your value is 2. When x is greater than 0, then you are this equation of x plus 2. So the first thing is learning how to evaluate. So the first part, it says, find the value of f of negative 2. So what's f of negative 2? That means your x value is negative 2. So what you're going to do is actually look at the domain and see which equation am I going to plug it in, to the first, the second, or the third. So where does x of negative 2 live? It lives right here. Negative 2 is less than 0. So I'm going to have to substitute it into the first equation. So f of negative 2 is 4 because that's the function that it satisfies in that region. What about f equals 0? F is equal to 0. That means x is equal to 0 here. So the answer is just 2. There's nothing for you to plug in. That just follows that equation. Any questions on just knowing where to substitute it? So that's just the first part. Where do I have to plug in x equal 3? The first, the second, or the third?
The third.
The third one. Why? Because 3 is greater than 0. So then I'm going to have to find, okay, well, f of 3 is going to be 3 plus 2, which is 5. So I'm going to have a few points. I'm going to have the point negative 2, negative 2. Sorry, negative 2 over here, negative 2 comma 4. That's a closed dot. I have the point 0, 2. I have the point 3, 5. So I'm going to put those right now. Negative 2, 4. I'm going to put 0, 2, and I'm going to put 3, 5. But I need to be very careful on how do I put them. Okay. Why? Because f of negative 2 here, this is less than 0. So I'm going to put in a parabola shape like this that starts here, actually. So at 0, so if I plug in, I can't plug in a 0, but 0 squared would be 0. At negative 2, it'd be 4. So I want to show you how how the graph is going to look like. Then remove this. So that's an open dot here. This is a quadratic. This positive 2, 2, 2, 0. This is by itself. This is this one, this point. And then if I am 0, 0, 2 right here, this is a line that looks like this. And this is the equation x plus 2. This one's x squared. So this equation is an x squared. Then I have this red point by itself. Okay, right here. And then I have from to infinity on this equation. See, so there's 3 pieces. Piece 1, piece 2, and piece 3. So piece 2 is just this point. Okay, so because this point is 0, 2. So the domain of this equation is from negative infinity to positive infinity. Those are all my x values. Okay. The intercept The only intercept is at 0, 2. Not at 0, 0. You don't have a point here. It's not valid at 0, 0. Okay. And then there's the graph. So the graph is the piece 1 is a quadratic. This quadratic. The piece 2 is the point. So the 0, 2. When x is 0, my y value is 2. The next one is when x is greater than 0. So if I plug in 0 plus 2, that's a 2. So from 2 to infinity, here's the other point that we found. This was the point 3, 5. So that corresponds to a line going upward. Okay. So this is called a piecewise function. Any questions on how I graph this? Questions on example 1? How do they have a different shape depending on the domain? That's important. Sorry about that. Okay. So let me put this through. I don't know what's wrong with this. It's not letting me do it. Okay. I guess because there's somebody's calling me. 1 second. It doesn't want to load. So let me stop this share. And let me share my other screen. Okay. So for the next part, if we're looking at, let me download here. Let me open my notes on this one because it doesn't want to project. There it is. It should now project. Okay. So we're back here at chapter 1. And then it's asking us to find the range. So the range, notice that the lowest point, what would be the lowest point actually? The lowest point would be 2 because 0 doesn't exist. So the lowest point would be at positive 2. So that's an absolute, here, this one's a minimum. The lowest point is 2 and the greatest is to infinity. So remember, the lowest point would not be 0. So this 0 is an open dot. Okay. Why is this open? Because if I try to plug in 0, it has to be less than 0. So we're looking at the values to the left of 0, not counting 0. So this is discontinuous here. Okay, so we found the graph and we found the range. And then has a bracket at 2 because it's including 2. We're going to do the same one with different problem, and we're going to do it together. So if we want to find f of negative 2, where does negative 2 live? In the first equation, second equation, or third equation? Where does negative 2 live? So x is negative 2. So if I'm looking at the domain here, where does it live? The first, the second, the third, which one?
The
Where am I
first.
in? Yeah, thank you, Leo. The first, right here. So it's going to be negative 2 times negative 2 plus 1. That's going to give me 5. So the first point I have is negative 2, positive 5. Negative 2, positive 5 right here. I know that this graph is a line. I know that because this is a negative 2 to the x, and it's going to go downward. It has a downward slope. What about f of 1? Where does that one live? When x is 1, what is my y value? My y value is 2 right there. So my y value is 2 if x is 1. So I already know that if x is 1, my y value is 2. And that's going to be a point like we had last time. So 1, 2 right here. That's a point by itself. It's its own point. And then x squared if x is greater than 1. So f of 2. So f of 2 is equal to 2 squared. I'm plugging it into the third equation. It's 4, so 2, 4. Okay. So now, again, to know the domain, I'm going to graph it. So the first thing I'm going to do is I'm going to be substituting my endpoints. So I'm gonna do the endpoints. I'm gonna substitute the endpoints. So I'm gonna do f of -3, and then I'm gonna do f of 1. So this f of -3, if you see this, this is a less than or equal to, so it's gonna be a closed dot. So when it's an equal to, you have it a closed dot. So -2 times -3 plus 1 is 7. So we have the point -3, 7 to be a closed dot. When I plug in a 1, it's going to be an open dot because it's a less than. We don't have equality. So it's going to be an open dot. So we have -2 times 1 plus 1 is going to be -2 plus 1, which is -1. So the point 1, -1 right here, it's an open dot. So this is going to go like this. It's a line. And it, I suck at drawing, so let me make this a little bit better. I want to make a line from here to here. Let me make this. And it should be touching this point. So let me make this nicer. So at -2, we said it was 5. And this is an open dot. So this graph right here is -2x plus 1. And it's a downward slope. A 2, 1, this point, 1, 2, it's a point that looks like by itself. This x squared is a quadratic. What happens if it would start at 1? If I plug it in, if I do f of 1 to this equation, it's 1 squared, which is 1. So this is an open dot. Again, it's not closed because we don't have equality. The only one that's going to be closed is when we have a less than or equal to or equality. So the 0.11, it's an open, so this would go like this. And this looks like a quadratic shape. This is x squared. And this little point, it's by itself. So you're divided into 3 pieces. You're divided by this -2x plus 1, the point, and then we have this quadratic of x squared. Okay. So when we're looking for the domain is from left to right. So from the left side is -infinity. I'm coming from the left. And then it stops. Okay. So see how it goes on all the way to +1. Okay. When I plug in a 1, what happens? I get a 2 right here, but then I pick it up. Okay. So I have -infinity. It stops here at 2. And then I'm going to go union from 2 to infinity. So I have to be careful because you don't start right here. So see how it stops here at 2 and then it picks it up again all the way to infinity. So you're not lowering down this x. So because you already started from -infinity and then you go all the way to 2 for your x. Okay, so -infinity to +infinity. But there's a gap right there. There's a jump of discontinuity. So see how they're all separated? Okay, so I have to count that separation here at 1, 2, and then again from 1 to infinity. Sorry, this should be a 1 because I'm looking at the x, not my y. So there's a jump of discontinuous at the value x equal 1. So that's why we have to make sure we separate it here at my x value being 1. Okay. What about the intercepts? Did we have any intercepts? No. No x-intercepts, no y-intercepts. Well, potentially this one, this one has an x-intercept. So if we would want to find the x-intercept would be a -0.5. So looking at this equation, Okay, so it can't touch 0, but it can touch this negative a half. So negative 2x plus 1 equals 0. If we subtract a 1 and divide it, we get at x equals positive 1/2. We should get a y-intercept. So this is, let's see, a -2. When I plugged in the -2, when I plugged in a 1, positive 1, we get 1, -1. So let me fix that. So this should be 1, -1. So let's fix that. So there's a mistake here. This should be an open dot right here. So this goes like this. So we have a x-intercept at 1/2. So at 1/2, it's crossing. Okay. So see how there's 2 points that are open and 1 that is closed. That's why we have that jump of discontinuity. So the x-intercept is at 1/2 and no y-intercepts. And then here's a graph of f. So we have a linear equation that goes down. Then we have 1 point at 1, 2, and then we have this quadratic x squared. So what I'm going to do is I'm going to actually send you guys also a Desmos link where you guys can play around with the piecewise functions and the domains for you to see more graphs. Okay. What about the range? So what would be the lowest point and the highest point? Well, the lowest point would be here at the value 2. At the point, the value 2 to infinity. So because this is by itself, this little 2, this 2 point. So 1, 2, that's the lowest point, and the highest point would be infinity because your graphs are going upward to infinity. Okay. I do want to talk about this application problem, which I think it's difficult. And I want to be able to discuss it. So in May of 2016, Commonwealth Edison Company supplied electricity for residents for a monthly customer charge of $7.58 plus 0.0825 per kilowatt for the first 400 in the month and 0.0628 per kilowatts for over 400 kilowatts. What is the charge for using a 300 kilowatts in a month? So you have a piecewise function. How do I know? Because you're separated by 2 different domains. So the first domain is you're getting charged $7.58 plus 0.0827 per kilowatts for the first 400. So if you go over 400, you're going to get charged more and it's going to have a different equation. So if we're using the 300 kilowatts, it's going to be the $7.58 plus the 0.08275 times the kilowatts. So this kilowatts was $300, 300 kilowatts per month. So that's why I have to substitute 300 here. When I substitute this, the good thing is that you're able to use a calculator. So it's 7.58 plus 0.08275 times 300. That breaks down into 24.825. When you add that, you get 38, you're getting charged $32 with 40 cents or 41 cents. So you want to round to the nearest, excuse me, to the nearest cent. So it's going to cost $32.41 to for 300 kilowatts. Now, the tricky part is what happens when you go over. So because you're going over by 400, sorry, by 300, it's saying for the first 400, excuse me, there is another equation. So if you're more, 400, like this case, you will use the equation 0.06208 times the kilowatts times X, and then plus the value of this 7.58 7.58 plus this 0.08275, and then you still have to do this x minus 400. Where did I get this x minus 400? Because you are exceeding. We want to know how much you are exceeding it by. So here you could do x minus 400. Okay. So you could do this both ways. Do it automatically. So you can plug in 0.0628 times 700. And then when you combine this 7.58 plus 0.08275, and then you multiply 700 minus 400. So let's do that on Wolfram Alpha. So there is this device, go to Wolfram Alpha. Let me share my screen here in a moment. Are you guys all looking at my Wolfram Alpha?
Yep.
Yeah.
So what I is this 0.06 208 business times the 700 kilowatts. And then because that's the rate that I have to use, plus the 7.58 of the additional, plus this 0.08275 times the 700 minus 400. Why am I subtracting? Because I want to know the difference of that. So that should give me, so I have this 0.02 times 700. Yep, this 759, this additional rate. Let me remove that. I'm missing a point. And then here, this plus 7.58 from the original. So it's saying that it would cost you $75.86. Okay, when you plug it in. Now I want to show you how can you separate it. Okay, so here, letter C, if C is a monthly charge, you develop a monthly charge that you want to use per hour. So this one is the initial when you are using up to 400 kilowatts. What happens if your X greater than 400? Okay, so then that's where you use this 0.06208 times X. Okay, plus the difference. Okay, that we found because you're passing the 400. So we use the 7.58 plus 0.0. So this is the initial. Okay, so let's go back to our Wolfram Alpha. Okay, I want to show you really quick. So this one was using the 700. But if I'm using the original model, so I have my 0.06208. Let me see if I'm using that correctly. And then that's X minus 400. So here's the 700 minus 400. Yeah. Plus the original, this 0.08275 times the original plus 758. Okay. And that's going to give me 59. So there's something, my calculations are wrong. I have to double check for mine. Let me share my screen. So the original piecewise function is this one, 7.58 plus 0.08275x. That's when you are generating between 0 to 400 kilowatts. What happens when you are increasing to more than 400? Let's look at the question. So you have for the first 400, there it is. And so you're going to have to add the remaining over 400. So that's what we had initially. So it was, you're going to take this and you're going to add it to this plus 0.062, what was it? 0.08, and then the X minus 400 business. So let me fix that. So you're going to use what you had on the initial plus whatever you go over. Okay. So that's why we have X minus 400 on this side, or X greater than 400. This piecewise function is represented in this problem. So based on the question, so it's saying 7.58 plus this 0.08 kilowatts for the first 400 kilowatts. So those are for the first 400 plus, so it says, and 0.0608 per kilowatts for all usage over 400. So you still have to add whatever you do, the extra. Okay. So so for the top part, let me just fix it. And let's apply the formula that I have here into our Wolfram alpha. So if now X is 700, okay, we're going to be applying our first 400 here because that's how much it's going over. And then here it'd be 300. So now if X is 700, so you went over 300. So what you're going to use is you're going to use your model, your 758 plus 0.08275 times your 400 plus this 0.06208 times 300. Why 300? Because that's 700 minus the 400. And that's what I'm going to be substituting into the Wolfram alpha business. So there's 0.06208 times 300 plus, there it is, this 0.0275, 400 kilowatts plus 7.58. So that's how much it's going to cost me. It's going to cost $59.30. So if you're using 700 kilowatts, then that's how much I'm going to get cost. Okay. So I have to be very careful when I substitute here my piecewise. So this C of X is represented by two functions, the original function, and then when you go over. And what I care about is actually my domain. So I know it's a lot, just digesting this and separating them by domain. But how do you guys feel about this application problem? It can get kind of tricky. Everybody? How do you guys feel about this one? So? Yeah, it's a little bit heavy. So the more you do, the better you'll feel. So on your homework, please make sure that there's also an option for view an example. Have you guys all tried that?
Oh yeah.
Yeah. And there's also, I do want to pinpoint that there's also recordings where they do application problems. So I'll make sure that I'll redirect you there too. Just because I know we're running out of time and I want to be able to maximize our time efficiently. So we're going to get to sections 1.5, which is graphing transformations. So we already know our basic quadratic function, y equal x squared. We know that's a parabola. So what we're going to be doing is we're going to be shifting our function, and we're going to be using Desmos a lot for this section. So on the same set of axes, sketch the graph x squared plus 2. So what's the difference between x squared and x squared plus 2? If I would put these on together, this x and y, so -1, 0, 1, and 2, when I plug it in, I get -1 squared, I get a 1, a 0, a 1, and a 4. If I add a 2, this will automatically bring my y value up to units. So it's now going to be 0, +2, 1, 3, and then 4, 7. So it moves, it vertically shifts to the right 2 units. All of my y values, it brings it up 2 units. This is my regular quadratic, and this green one is x squared plus 2. So see how it brings it 1, 2, 1, 2, 1, 2. There is a vertical distance of 2 units, 2 units up, 2 units up, 2 units up all the time. That's what this x squared, the plus 2 on the outside does. So test your connection by predicting the graph of y equals x cubed minus 3 and then graphing it. So what we know based on that first part, because we added 2, it went up by 2. What happens if I subtract 3? Then it will go vertically shift down. It would vertically shift downward 3 units. And I'll show you that on Desmos. So going to Desmos here, I have x squared, and then I have x squared minus. See how we started at 0, 0, and now we're 0, -3. It brought it down. So from here to here, from 2 to 4, oops, where's 2 to 4? There it is. So from 2 to 4 down here. So see how they bring it down 4 units. So from here to here, down, it shifts down your parabola from here to here. So the vertical distance now is -3. Okay, you're subtracting 3. So the transformation, whenever you see a minus or a plus, see if I do an x squared, an x squared, if I do plus 8, it brought it all the way up 8 units. So from 0 all the way to 8. So it went vertically up 8 units because of this plus 8. If it's on the outside, it moves vertically up or down, depending whether it's a plus or a minus. So that is the first transformation that we see. So vertical shifts, if a positive real number k is added to the output, y equal f of x, the graph of the new function will shift upward k units, upward vertically k units. If you are subtracting the output, so now if it's f of k, f of x minus k, then it's going to be shifting down k units. That is the first, and that is called a vertical shift. And it works with all of the functions. I could show you a new function. What if I ask for, I don't know, maybe the square root of x, and then on the outside I do a -3. See how the original, the x square root of x, see how from 0 it went down to -3, it went down 3 because of this -3. If I take this and if I add a 3, now it goes up by 3 because of the +3. So see how it shifts vertically up and down? So that's the first, that's the easiest one. That is the easiest of the transformations. So now what if we have a horizontal shift? I'll talk about that in a moment. Exploration number 2, this is the other type of transformation. 2 functions f and g are related by the function g of x. This x minus 1, it means it's a horizontal shift to the right. So what I'm going to do, so see how the value I have the value of 2, it shifts vertically. So if this point is 2, 0, now it's going to be 3, 0. If this point is a -2, it's going to go to a -1. And this point, this -1, is going to go to 0. It's shifting to the left 1 unit because it's on the inside. So what we did is we took each of the graph, the original, let me remove the red one. So we start by looking at the original points. I have a -2, 0, I have a -2, and I have a -1. So then now I'm going to shift to the right. So now it's going to be a -3. My X value, so my Y value doesn't change. The only one that changes is the X. So I add 1, becomes a 3. So 3, 0, 3, 0. At the value -2, I'm going to shift it to the right. Right here. It's going to be now a pause from 0 to 1. And then from -1, it's going to go to 0. And it's going to have the same thing. So what happened is that this shifted 1 unit to the right from the given point. So we shift to the right 1 unit. So if that happens when it's X -1, what happens when it's a +2? Well, now you go backwards because it's a plus, you shift to the left 2 units. So again, looking at the original, let me erase this. I start with this point 2, this 0, and this 1. For the X, I'm only switching the X. The Y values will stay the same. If I'm shifting 2 units to the left, instead of being 2, now I'm being 0. This 0 will become -2, and this -1 will be 3. So the graph will now look like this. I just said that the Y values do not change. The ones that change only. So see how I shifted 2 units to the left, 2 units to the left, 2 units to the left. So I switched this orange to the green, this orange to the green, and this orange to the green. Okay. So this means you're shifting 2 units. So see how this was -2, now it's going to be -4, -1, -3, 0, negative. So look at the X's. Subtracting a 2, subtracting a 2, subtracting a 2, subtracting a 2, subtracting a 2. Because you're shifting to the left 2 units. So these are called horizontal shifts. I will go more in depth with an equation so you can visually see that on Desmos as well. So if the argument, meaning the inside of the function, is replaced by X minus H, then you are moving to the right H units because there's a subtraction. When there is an X plus H, you're moving to the left H units. That is called a horizontal shift. So we looked at a vertical shift and we're looking at a horizontal shift. So I'll let you write that down while I go to Desmos and then I'll show you what I mean. Okay, let me share my screen. So the first one is my quadratic X squared. Because I moved X minus 2 is on the inside, there is a horizontal shift to the right 2 units. See how this one moved? From here to here, this one moved. Let me give you, it's not the same as X minus 2 on the bottom. See how it matters if it's inside or outside? It does. Let me show you a different one. What if it's an X plus 4 squared versus an X squared? See how it moved now to the left 4 units? From here to here, from here to here, it moved. It also moved. Look at -4 and -6. See how it moved 4 units? If I subtract -2 minus 4, you get -6. It moved to the left 4 because of the x plus 4. That is called horizontal shifting. We could apply it to another function. Like what? Like the square root function. So if I have the square root of x versus, what happens if I have the square root of x minus, but in the inside, I have to put parentheses x minus 3. See how it moved to the left 3 units? Sorry, to the right because of the minus. What if I do that, but now with a plus? Where will it go? It'll go to the left. See how the x values change from 0 to -3 because of this one, and a +3 because of the horizontal shift. How do you guys feel about horizontal and vertical shifts so far? Whether it's on the inside or the outside. Are you guys okay with that? How do you guys feel?
Yeah, that's good.
Now, we are going to talk about, there's more things that we can do to a graph. The next thing is stretches, a vertical stretch and a vertical compress. So look at the exploration number 3. The original function is my x squared, which is the red one. What happens if I multiply it by a factor of 2? It's going to stretch it. It's going to have a vertical. This will have a vertical stretch. So meaning that it goes faster to infinity, whereas 1/2 x squared, it's going to be wider. It's called a vertical compress. So if you have a value a greater than 1, this is going to be a vertical stretch. But it has to be on the outside, a of f of x. If a is a fraction, meaning in between 0 and 1 of a of x, this is going to be a compress, a vertical compress. So there's a vertical stretch where a is greater than 1, like 3, 4, 5, 6, it's going to go faster to infinity. Whereas if you have a fraction, it's going to be closer. It's going to be a vertical compress. So similarly on Desmos, if I share my screen again, look at my square root of x. Let's compare the square root of x with what happens if it's 5. See how it stretches vertically up? And what if I have this 1/2 the square root of x? See how it's a vertical compress? So you press it down, so you vertically stretch it or you compress it. So this, because 5 is bigger than 1, it's going to be a vertical stretch. And this one is going to be a vertical compress. I can do another example. I can do the absolute value of x. So there's the absolute value of x. Oops. What happens if I am 5? See how it's stretched? The 5, and what if it's 1/5 the absolute value of x? See, look how it compressed it down. The other one stretched it up. So here are the two differences. One is a compressed down, the other one is a stretch, vertical. Okay. So going back to our notes. The summary. When, as I mentioned, when you are the a between 0 and 1, like a fraction, it's going to compress vertically. When a is greater than 1, it's going to be a stretch. Okay. Now look at the difference between this one. So I want to make sure that I have the right one first. So assuming that we have this 1/2 of x. So we know that g is 1/2 of x. So let's start by substituting -4 into the function. So g of -4 is going to be f of 1/2 times -4. But what is f of 1/2 times -4? That's f of -2. F of -2 is +2. So -4, +2. When I plug in f of -2, sorry, g of -2, because I'm working with the g function right here. That's going to be f of 1/2 times -2. That's going to be f of -1. But f of -1 is 0. So if I'm at -2, I'm now at 0. At 0, when g is 0, f is 0. So that's at 0, -2 right here. And then when I'm at 2, that's going to be f of 1, which is -1. So 1. So at x being 2, I'm at -1 right here. So then my graph, and then I'm missing one more. When I'm at 4, so 2, -1, and then I have 0, -2. So -4, 2 right there. I have -2, 0. I have 0. I think I missed this one. Sorry, 0 at -2 right there. 2, -1 right here. And then 4, 0. So when I plug in 4 to this equation, 1/2 times 4 is f of 2. F of 2 is 0. So look at what's going to happen to the graph. See how it pushed down? There is a compress. You're compressing your function down when you are 1/2. When this is a fractional power, you are going to horizontally compress. This is called a horizontal compress. So there is a vertical stretch, a vertical compress. There is a horizontal stretch, horizontal compress. And that's what happens here. So similarly, when you are substituting the value of -2 here, f of -2 is f of -4, but we don't have -4 here, so we don't have a value there. When I plug in a -1, f of 2 times -1 is f of -2. F of -2 is +2 right there. So I have a negative, let me erase this. So we have -1, +2 right here. So that's when it's going to start stretching. When I'm at 0, f of 0 is -2. When I'm at 1, f of -2 is 0. And then when I'm at 2, f of 2 times 2 is f of 4, but I don't have f of 4. So those are the only points that I have. So what it did was it stretched, it horizontally stretched. So we have two things. We have horizontal compress and we have vertical stretch. So here how we have a fractional power between 0 and 1, that is going to be a stretch. When a is greater than 1, it's going to be a compress. I only have, so the time is past. It is obviously 9. But I am obviously going to send you these notes where you guys can play around with Desmos and send you more additional support Just because we did go over questions or sections, excuse me, 1.1, 2, 3, 4, and this would be the fifth. That's 5 sections, which is a lot to cover in 1 week. So, I'll be sending you guys these notes completed, of course. And then, I'll send you the remaining videos. In reality, there's 6 more pages to go to finish the section. So there was 1.6, which was really short, and then 1.7, which is literally 2 pages. So I'll be sending you guys these videos and recordings for the sections. But the largest part or the biggest part that was needed was all the way to section 5, which was the last this last part that we are completing. So just noticing, we kind of did talk about symmetry across the X, across the Y, symmetry towards the X, whether it's on the outside or the inside, that matters. Looking at the horizontal reflections or vertical reflections. And this is just a summary. So once you have the summary, it'll be good to go. Okay, and then just playing around with the functions. These you can do on Desmos. So just looking at the reflections and what we can do. So I wouldn't stress too much because you can use Desmos so you can have a visual, at least a visual representation to help you with that. Okay. Do you guys have any questions in general of anything before we stop the lecture? So I'll stop the recording now.